Welcome to PEEC's live stream astronomy talk, The Age of the Earth and How We Know It by Galen Gisler. Galen was born in Clovis, New Mexico and graduated from high school there. With a PhD in astrophysics from the University of Cambridge, he eventually came to Los Alamos where he worked at the lab for 25 years. Then he and his wife Susan moved to Norway where he learned not quite enough geology at the University of Oslo, finally retiring back to their cozy mountain town here. The PEEC Planetarium is his favorite place to spend time, so he's eager to get back to it when this time of isolation is over. Galen, I'm going to turn it over to you.
Thank you very much, Siobhan, for the nice introduction. I'm glad to be here. I wish I was in the planetarium doing this show, but we can certainly do it from home, and that's what we're going to do this evening. So I'm going to talk about the age of the Earth, and the questions that I'm going to pose are: one, has the Earth lasted forever, or did it have a beginning? And if it did have a beginning, then when was that beginning? So it might seem strange to start a talk about the age of the Earth with a slide like this, which basically illustrates the seasons. But I'm making a couple of points with this. One, I want to connect a little bit with Rick Wallace's talk last week, where he pointed out how the seasons occur. That was his talk for the spring equinox, and also to point out that things that we normally do are cyclic in nature. And in fact, I gave a talk last month that some of you may have been at on the calendar and how we use astronomical cycles in order to measure time. And of course, measuring time is what we need to do if we want to measure the age of the Earth. But cycles are also important in another way, which I'll get into as the talk goes on. So this, of course, is the annual cycle of the Earth, and we also have cycles that go daily and monthly. These are an example of tides at Bridgeport, Connecticut. And then, of course, our journey through space. As the sun moves through the galaxy, the Earth moves around the sun, and the moon moves around the Earth. And all of these things these motions can, in principle, continue indefinitely because they're governed basically by conservation laws of physics. But we know that processes don't necessarily go on forever, that things can interrupt processes that might otherwise be going on forever. And the question is, how far in the past can we trace processes like these cycles, and what can that teach us about the age of the Earth? So one cycle that I want to talk about, a couple of cycles that we're pretty much familiar with here on Earth. And one is the water cycle, where evaporation from the ocean produces eventually precipitation from rain clouds over land or over ocean or whatever, and you get this continuous cycle that brings the water eventually back to the ocean from which it began, either through surface runoff or through groundwater runoff, and you have a number of subloops going on in here. And in principle, this is a closed system. The only thing that keeps it going is the energy input from the sun. Given the energy input from the sun, this cycle could continue more or less indefinitely. Another cycle, which is slightly more relevant to the questions of this talk, is the rock cycle. So deep in the Earth, rock gets heated and melts, becomes magma. It crystallizes and can become igneous rock. That igneous rock can be exposed to the surface and be subjected to forces of erosion by water or wind. The products of that erosion are sediments, which are deposited in the ocean or in lakes or in rivers or whatever, and that becomes sedimentary rock. The sedimentary rock can be buried tectonically and be transformed into metamorphic rock, and that metamorphic rock on further burial can melt and the cycle begins again. And again here, there are subloops as well. Igneous rock can go directly back to melting or to metamorphic rock. Sedimentary rock can likewise be eroded yeah, so there are a number of these subloops that can go on and on. And again, this can go on indefinitely, but it requires an energy source, and that energy source is the mechanism by which rock is melted into magma. So here's a diagram that kind of combines both the water cycle and the rock cycle, and you can see it laid out more completely here, or more diagrammatically, where you have erosion from the land depositing sediment into the water, and then it's buried in compacted sedimentary rock. As it is subjected to intense pressure, it deforms, metamorphoses, eventually melts, and it comes back up through the surface, either through volcanoes or crystallizes, and is buried as plutons and is weathered and so forth. And but the water cycle is important here too, in that it facilitates the movement of sediments and so forth through over and through the land. So the rock cycle and the water cycle, the heating from the sun and the heating down below from the internal heat of the earth, all of these things together make the Earth an active geological planet. The tectonic uplift here is also driven by the internal heat of the Earth, and then the deposition of sediments into the ocean brings dissolved solids from the land into the water, and increases, for example, the amount of dissolved salts that are in the water. And so all of these processes go on, but these processes have consequences, and those consequences can, in principle, be measured. So here is an example of sedimentary rocks. In fact, these are chalk layers on the island of Cyprus. And you see lots and lots of layers here of somewhat uniform or non-uniform thickness, depending. I mean, it's, some of the layers are thinner than others, and some of them are thicker. But it looks, again, cyclic. As you know, this layer was laid down, then there was an interruption, and this layer was laid down, then an interruption, and this layer, and so forth. And so here also we have an example of a cyclic process, which goes on presumably at a much longer time scale than the processes that we've been talking about so far, the processes of the Earth's motion around the sun, or the moon's around the Earth, or whatever. So what causes these cycles? Perhaps it's changes in sea level through glaciation. The Milankovitch theory ties this to an astronomical effect, namely the precession of the Earth's orbit and so forth. I'm not sure that in this particular case what is involved, but anyway, I mean, you get the impression that a lot has been going on here, and it's been going on over a very long time. I don't know if you can count the layers here, but there are certainly dozens of them, and they don't necessarily end at the surface of this road. They go on probably a good deal further down beneath. So this tells you something about the processes of through time that have produced this particular feature on the island of Cyprus. Another example of this sort of thing, which is much more familiar to us, is tree rings. Now, of course, we know about these. These are annual in nature. We have a period of long growth and a period of virtually no growth, long growth and no growth, and so forth. And this is on an annual basis. And so you can measure the age of a tree by counting the tree rings. Is it possible that you can measure the age of the Earth by counting the layers of sediment in a place like that cliff on Cyprus? Well, I don't know. in the first place, you don't know how long it takes for each of those sediment layers to be accumulated. For another, as I mentioned, you don't know how much farther into the Earth those layers extend. And you don't know what those interruptions are. And there might be even more, and indeed probably are, even more severe interruptions than the ones that we saw in between those little layers. So that prospect is rather dubious. Nevertheless, there have been attempts dating as far back as Herodotus in the 5th century BC to make an estimation of that. So Herodotus asked the question, how long does it take to build the delta of the Nile? In principle, you can measure the amount of sediment that's transported by the Nile every year. You can measure the extent of the delta in both dimensions. The other thing that you would need to know how to do, which was unavailable to Herodotus, is to measure the depth of those sediments underneath the surface. The Nile Delta is built up yearly by these very reliable floods, and in fact, the Egyptians based their calendar on the flooding of the Nile. They knew it happens every year, and Herodotus just reasoned that because sediment was being carried down, that this delta had to be built up over the period of time that the Nile was in existence, carrying stuff down towards the sea. He asked this question, but he wasn't able to answer it. So over the years, people have tried to make estimates of how old the Earth is. The Greek philosophers tended to think that the Earth was infinite, that they saw these cycles going on and on and on for millennia, and they figured they must have been going on forever and ever before that. The Hindus made a chronological estimate that the Earth was 2 billion years old. I don't know exactly how they came up with that figure. Theophilus of Antioch was the first one who used biblical chronology in 169 of the Common Era, and his method is familiar. Of course, he basically takes all of the genealogies in the Bible and counts them up. It's not a ridiculous way of doing things. It's scientific in a way because he's going back through the most complete documentation that he had of the time and trying to count it all up. The problem is that he could bring no secondary independent evidence to bear on that number. Starting in the late 18th century and continuing through the 19th century, there were a number of more scientific estimates of trying to figure out how long the Earth had been in existence. Benoit de Maillet thought that the seas were continually decreasing, that sea level was continually declining, because he could see that certain pieces of land were now above the sea, which were formerly before, because they had fossils of sea life, marine life in them, and he estimated by that technique that the Earth was something more than 2 million years old. Lord Kelvin, and I'll get to this a little bit later, made two different estimates during the course of his career. One was 20 million years and the other was 400 million years. And I'll talk about this a little bit more later on. Then the sediment accumulations, Thomas Huxley estimated 100 million years for all the sediments in the geological record to be accumulated. George Darwin, a cousin of Charles, looked at the tidal effects of the Earth and the Moon, and we know that the Earth's rotation is slowing down because of tidal effects by the Moon, and also the Moon is drawing farther and farther away from us, and so he basically extrapolated that process back into time, and said that it had to be somewhat more than 56 million years old, but not much more. And then the salt in the ocean, measuring how much sodium there is there, and estimating how much is being carried into the ocean by rivers. Jean Joly estimated that it was about 90 million years. So we have these estimates of sort of few millions to hundreds of millions of years that were prevalent throughout the 19th century. And there were lots of arguments about this. And at the same time, of course, people were starting to look carefully at the fossil record. Now, fossils had been known about, since ancient times. Aristotle remarked that fossils are the remains of animals that lived long ago. Very matter of fact remark. He sort of implicitly believed that animals evolved from more primitive to the more advanced. He didn't have a mechanism for doing that. That had to wait until Darwin came around. But fossils were well known in those times, and it was well known that things like trilobites, which exist in the very lowest levels of the sediments, were creatures that had no counterpart in the modern world. The Persian philosopher Avicenna had an interesting view, saying that petrifying fluids were the cause of the production of fossils, but again, echoing Aristotle that this was from ancient life. And Leonardo da Vinci agreed with Avicenna about this petrifying fluids, and he also noted, because of the distribution of fossils around the world, that he doubted that they could have been deposited by some kind of a global flood. So then we come to how the science of geology was established. Up to the 17th century, all of science was called natural philosophy, and there were no divisions between the different aspects of science. It kind of started with Nicholas Steno, this Danish scientist who proposed the principles of geology, talked about superposition, how layers are deposited one on top of another, and how there are these cycles of deposition and erosion. Robert Hooke talked about fossils, and the idea that you find different fossils in different layers gave him the clue that he could use fossils as a basis for chronology, actually establishing some sort of a relative timetable for the deposition of the sediments and so forth. And then Bernard de Maillet again talked about sedimentation and weathering as very slow processes. But then we come to James Hutton, who is a real turning point in the history of geology and in the history of the age of the Earth. There's this very famous place that he visited together with John Playfair. He actually was sailing by this point, and he told Playfair to stop, let's get off the boat and look very closely at this rock formation. It's a little bit hard to read, but what you see here are stratifications here going in this kind of direction, and then there's a sudden break right about here, and then you see stratifications going in more or less vertical direction. And this is called Hutton's Unconformity. The remark that John Playfair, who was the boat driver, made was that the mind seemed to grow giddy by looking so far into the abyss of time, because Hutton and Playfair knew that each one of these layers here took a very long time to be deposited. And then there's an unknown length of time represented by this gap, this unconformity. And then each of these layers took a very long time to be deposited. So that was what he meant. The mind just grows giddy at contemplating the abyss of time, the notion that time is very, very deep, and that we live on the surface of something very profound. This is a picture of the Hutton's Unconformity in a different location where it's laid out more clearly, and it's a sketch, an engraving that this fellow John Clerk made. And here you see the layers at the top, nicely ordered and so forth, and then the layers, this unconformity, which is a real mess, and then these vertically oriented strata down below, all contorted and so forth. But it's this is about 30 miles away from the point on the shore of Scotland where that very famous outcrop exists. The next guy that I want to mention is William Smith, who was working in some coal seams in the southwestern part of England. And he also worked in other coal seams in other parts of England, and he noted that the same kind of strata occurred in different places. And then it took him some years, but he eventually produced this extremely detailed and beautiful map of all the geological strata of Great Britain. And he identified strata, for example, this blue one, by finding the same fossils in this location, in this location, in this location, all the way along there. And so you could tell that this strata was deposited at about the same time, even though right now it's exposed on the surface in these very different places and twisted around, contorted in all kinds of strange ways. An example of the violence that has taken place in the geological history of the Earth. I happened to read this book by Simon Winchester, The Map That Changed the World, a few years ago, and that was one of the things that really started piquing my interest in geology. Very good book. I strongly recommend it if you're interested in following up this subject. So the principles of geology that were laid out by Nicholas Steno and then amplified by the other people are that in the first place, younger layers lie above older layers. That's the principle of superposition. That the layers are laid down horizontally, so that if you see some layers that are tilted, that reflects a deformation that has occurred since the layers were laid down. If you see similar layers that are separated by some gap, the interruptions reflect faulting, sort of a violent shoving aside through an earthquake or whatever, or erosion by water or some other means. But you can paste those layers back together if you use your imagination a little bit and do some careful mapping. And then finally, that if you see faults and intrusions, those are younger than the features that are cut by them. And so here's an example, just a sketch of, so here's lateral continuity. This layer J is the same as this layer over here. There's been a fault that has moved them apart, and this fault has occurred after all these layers have been laid down. That these layers were originally laid down horizontally and then have been tilted. A real world example of this is the Grand Canyon, where you have quite an extensive set of sediments from the Mesozoic all the way through the Paleozoic and ending superimposed on these igneous rocks of the Proterozoic. And then at a couple of exposures within the canyon, you find this Grand Canyon supergroup, which is one of the rare examples of Precambrian sedimentary rocks. So this concept of deep time, which was developed by Hutton, Playfair, and all of these folks, led folks during the 19th centuries to start naming and sequencing the sediments that they found and associating them with names. And usually they used names of locations where they were first found, like Cambrian refers to Wales. Silurian does also. Devonian refers to the county of Devon in England, and Mississippian, Pennsylvania. Well, you know what those are, and so forth. the Jura Mountains and so on. The guys who were really instrumental in doing in sequencing and naming these things were Roderick Murchison, Adam Sedgwick, and Henry Thomas de la Beche, and they argued intensely about various sequences and so forth. In fact, there was a real fight that broke out called the Devonian controversy, that they couldn't convince one another that these were in fact 4 separate periods until someone else came along and settled the argument for them. But all of this is just relative dating. We weren't able to do any absolute dating until radioactivity was discovered. And I'll just put up the approximate numbers that we have now in millions of years, going back to say 540, 550 years for the beginning of the Cambrian, and then it gets more uncertain below that. But we'll talk a little bit about radioactivity a little later on. But first, I want to refer back to this point that I mentioned before, that in order for the rock cycle to work, you have to have an internal source of heating within the Earth. And this internal source of heating has actually been known since ancient times. I mean, ancient people knew of volcanoes and and hot springs and so forth. And I see something flashing at the bottom of my screen, or maybe I'm supposed to check the chat thing. Okay, right, good. So the ancients knew about the internal source of heat for the Earth, and they were puzzled about where it came from. They assigned it to demons or the devil or whatever. But as time got on into the 19th century, people had to start thinking a little bit more logically and a little bit more scientifically about what the source of that heat was. And a number of people came up with the idea that the Earth had started off very, very hot and was gradually cooling off, and that cooling off was producing the heat flux that was the engine for earthquakes, for volcanoes, for hot springs, and all of that sort of thing. But you can measure the heat flux of the Earth in different places. This is, of course, a modern map, but even in Lord Kelvin's time, it was commonplace to measure the heat flux of the Earth by inserting thermometers into deep pipes and measuring the temperature as a function of depth to get the gradient at the Earth's surface. The measurement of that gradient implied that if the Earth was once very hot, it was cooling off, and the rate of cooling off could be inferred directly from the temperature gradient near the surface, and would imply an age of the Earth from its original very hot stage of only 20 million years or something like that. And as I said earlier, Lord Kelvin actually revised his estimates a couple of times during his lifetime, partly because he realized that different spots on the Earth had very different temperature gradients, and also because he realized that different types of rock conducted temperature better or worse than other types of rock. So this was a real contradiction, because the geologists and paleontologists had a gut feeling that the Earth had to be a lot older than a few tens of millions of years old in order for all of those sediments to be deposited, and in order for all of the evolution to have taken place from very primitive life to modern life. So there's a real contradiction, and you know, contradictions often occur in science, and contradictions are useful in that they spur people to think and come up with new ideas. And the new idea that people came up with at the beginning of the 20th century was radioactivity. Radioactivity was discovered in the 1890s or so, and Rutherford realized that if there were radioactive elements deep in the Earth's crust, in the Earth's core, or anywhere within the Earth, the heat from the decay of those radioactive elements could contribute to the temperature gradient that we presently see, and so the Earth could, in fact, be a good deal older than Lord Kelvin thought. And also, of course, the sun could be much older because radioactivity provides another source of energy that the gravitational collapse was not sufficient for. So I'm going to show a little graph here. I'm only going to show two graphs in this talk, and they're both very simple graphs. So I hope you'll forgive me for that. This is basically to say how radiometric dating works. So a radioactive isotope, which we call the parent, decays at a certain rate, and the rate is an exponential decay in the number of atoms which belong to that parent. With each atom that decays, a new element, a new atom, the daughter, is produced, and so it rises as basically 1 minus that exponential decay, and so after what we call a half-life, exactly half of the original sample of the parent is gone, and it's been replaced by an equivalent number of atoms of the daughter element. And so, so this is how radiometric dating works. You compare the amount of a parent and daughter that's within a sample, which you hope is closed, or you can make corrections if it isn't, and then you read off from these lines how many half-lives have passed since the rock was formed, or whatever sample it was, and so you see after about 8 half-lives, there's virtually nothing left of the parent, and it all becomes the daughter. You can think of this pretty much as a sand glass and as an hourglass. So you have in the top part of the vial, you have the atoms of the parent, and in the bottom half, you have the atoms of the daughter, and you can tell how much time has elapsed by how much of the daughter there is compared to how much of the parent. So the relative quantities gives you the age of the sample, as long as that sample is self-contained. In other words, that the parents don't escape by other means, or the daughters don't escape by other means, or aren't introduced by other means. And so, for the most part, you can correct for those things under the appropriate circumstances. So the isotopes that are used for radiometric dating, and this is how we really determine the ages of rocks nowadays, are many, but these are the ones that have the longest half-lives, and you'll note that some of these are very, very long indeed. 106 billion years for samarium to decay into neodymium, 48, almost 50 billion years for rubidium, and so forth. So the very long half-lives, and you can measure half-lives fairly easily in a laboratory with relatively small samples, because there are, on the order of 10 to the 23 atoms of a particular element in a laboratory-sized sample, more than that, and all you have to do is count the decays through some sort of a radiation detector, and then noting how frequently those decays occur. It's a very simple formula to produce the half-life from those. So 2 things to note. One is how very long these half-lives are, so you can reliably measure ages that are of this order of years. And the other thing that I want you to note is the fact that we have these 3 decay chains, which produce 3 different isotopes of lead, all with 3 different half-lives. And they come from thorium and 2 isotopes of uranium. This will become a little bit more important later on as we get to some specific examples. The key mineral that one wants to look for when doing radiometric dating is zircon, zirconium silicate. It occurs in a lot of igneous and metamorphic rocks, and also as grains in some sedimentary rocks, if the sedimentary rocks have been produced by the erosion of metamorphic or igneous rocks. And the thing about zircons is that uranium fits readily into the crystal structure of zircon, but lead does not. And so when a uranium atom decays into lead, the lead is easily detectable. So this is extremely useful for radiometric dating. So in order to measure the age of the Earth, what we need to do then is look for the oldest rocks we can find. And where do we find those old rocks? I've been using a lot this book from Dalrymple, The Age of the Earth, and there was another book of his that I was referencing through this. Both excellent books. He's an excellent writer. This is the distribution of Archean and Proterozoic rocks. So Archean is the very bottommost layer of the geological column, and those are the dark ones here. And these Archean structures are called the cratons. Cratons are basically the original continents of Earth, or the fragments that remain from the very first continents that Earth had. There are 2 of them that I'm going to look a little bit more closely at a little bit later on. One is the Slave Craton in the Northwest Territories of Canada. One is the Yilgarn territory in Western Australia. But all of the oldest rocks that have been found in these several cratons, which exist on each of the continents of modern Earth. And here are some examples, and these were mostly found in the course of the last 50 years or so, and you see there's several that are in high 3 billion year old range, mostly dated with the uranium lead dating method, one the samarium neodymium, and the oldest one that is on this table, and as far as I know, at the point of its publication, it was the oldest one known at 4.03 billion years old. And that's in this slave craton in the Northwest Territories of Canada, in what's called the Acasta gneiss complex. And if you're interested in going there, that's where it is, a long way north of Yellowknife. I guess here's the Great Slave Lake, and here's what it looks like from Google. I believe the place where that particular sample was taken was right about there, and here is that sample, a fragment of that Acasta gneiss from the Slave Craton. You can visit it in Vienna at the Natural History Museum, and it's 4.03 billion years old. The other one that I'm going to look at is this one in the Jack Hills region of the Yilgarn Craton in Western Australia. Again, it's a long way from any place that you might know, way north of Perth. And here's a Google photo of that area, and the particular sample, I believe, was taken from right about there. And this is a single mineral, not a complete rock, but a single mineral from that from a rock that's there, and it was dated to a much older age of 4.4 billion years old. And yeah, there's a reference in case you're interested in looking that up. so the oldest mineral that we have on Earth is 4.4 billion years old. The oldest rock that we have on Earth is 4.03 billion years old. So we know that these are sort of lower limits. The Earth must be at least as old as that. And so we have to, but we can't find anything older on Earth. And so to find older things, we have to go off the Earth. And so, in fact, when you go to the moon, here is some 8 examples of ages that were found on rocks that were collected on the moon. One by the Soviet Luna spacecraft, the others by the U.S. Apollo spacecraft, and you get ages that exceed 4.5 billion years. This particular anorthosite that was collected in Apollo 15 was 4.59. I'm going to show you a picture of this anorthosite that was collected by Apollo 16, but first I'll take you to those places on the moon, and if we were doing this in the planetarium, I would actually fly you there to the Descartes Highlands, right here in the south central part of the Earth-facing surface of the moon, the Descartes Highlands, where Apollo 16 landed, and here is the Apollo 16 landing site is right about here, and the particular sample that I'm speaking of was collected about 15 meters southwest of that site. These lines are the traverses that the astronauts made during that excursion to the moon. Here's that sample, number 60025, an anorthosite dated to 4.44 billion years old, currently on display at the National Museum of Natural History in DC. Then you can go to meteorites that were collected on Earth. So they're not Earth-bound samples of rocks, but they're samples of rocks that have come from somewhere in the solar system, and you get ages that are similar to those ages that we've seen from the lunar samples. And many of these meteorites are pretty well known. Canyon Diablo is of course the meteorite that was collected from the Barringer crater site in Arizona. So probably many of you have visited that site. So I want to come back to this question of lead. So there are 4 stable isotopes of lead with mass numbers of 204, 206, 207, and 208. And I mentioned before that these 3 are produced from the decays of uranium, the isotopes 238 and 235, and thorium, the isotope 232, with half-lives that differ considerably. Lead 204 is not a decay product, and so whatever was produced of lead 204 is what remains now, but whatever was produced in the original synthesis of lead of 206, 207, and 208 had to have been increased by the decays of uranium 235, 238, and thorium 232. That's an introduction to a particular meteorite that I want to display to you now. This is the Nantan Meteorite, which people think was observed falling in 1516 in Guangxi in China. But it wasn't discovered until, it wasn't recovered, that is, taken out of the ground and sampled until 1958. So that link between the 1516 fall and the recovery in 1958, you're allowed to have some skepticism about that. What happened in the 1950s was that Mao Zedong was putting his Great Leap Forward proposal together and demanded that people out in the countryside go and scour the fields for iron. And in this one particular field, they found chunks of this meteorite, this one particular very large chunk, which is about a meter long and weighs several tons. The villagers couldn't do much with, and so they realized that it was something extraordinary, and handed it over to a regional museum. And then lots of scientific investigations have been done since the 1950s on this meteorite to try to understand its composition and so forth. And so let's come back then to lead. It turns out that there's a mineral troilite in this Nantan meteorite that has a fair bit of lead in it, and you can measure how much lead in comparison with how much of these other isotopes of lead in comparison with the 204 isotope exists in that Nantan troilite, and you can compare that with the abundance of these isotopes on Earth today. These abundances are considerably larger than these, reflecting the fact that that uranium and thorium have both decayed into these isotopes. These abundance ratios are in fact very close to the abundance ratios that are predicted from the nuclear synthesis in the so-called S process that was first proposed by Burbage, Fowler, and Hoyle in 1957. And so it's thought that these abundances are pretty much primordial, and so that the entirety of the difference between these numbers and these numbers is due to this decay. And since these half-lives are all different, you can use that to produce an age independent of all of the other ages that we've been talking about so far of the Earth. And so here's that other very simple graph that I'm gonna force on you, and it's basically a ratio of the 207 to 204 isotopes of lead and the 206 to 204 isotopes of lead. So it's 2 out of the 3 ratios that we could make with the 204, the primordial isotope. And here's a curve of growth. The 0 is the primordial abundance of these elements, of these isotopes with respect to the 204 isotope, and it's also, we think, the same as the abundance in the Nantan troilite. And then along this curve, in units of billions of years, we have these dots spaced, and down here at the lower left-hand corner is a dot corresponding to the present abundance of lead, both in the Canyon Diablo meteorite and also in ocean sediments on Earth. So that gives us an age of 4.55 billion years for both meteorites and the Earth. I think this is a very profound way of looking at this question of the age of the Earth, and probably the most reliable, because it can take from a single element and known half-lives, these curves which give you this unique age. So that's the conclusion. The Earth is 4.55 billion years old. The other things, the other estimates that we had for the age of the Earth up to this point in this talk have been, in a sense, all lower limits, in the sense that the Earth could be older than that. But this is a very firm age, so both a lower and an upper limit. Now I want to touch on one last thing, and that's in a couple of months back, in fact in January, this publication came out saying that silicon carbide particles in the Murchison meteorite are found to be 7 billion years old, considerably older than anything else that we've been talking about in the solar system. So, I mean, this is a brand new finding. I've only seen one citation to it in the literature. I think it probably needs to be vetted a little bit more. The interesting thing about this is that the grains that we're looking at are their age is determined by the cosmic ray exposure while this meteorite, while the grains rather were in the interstellar medium. So sort of independent of their eventual deposition in the solar nebula. So this tells us something about the environment around the solar system before the solar system was in fact formed, and is a very interesting finding, and I hope to hear more about it in the future. So then basically a summary. The solar system began forming 4.5 to 4.6 billion years ago. Planets formed by accretion of matter within the solar nebula. Earth was hit by a giant impact that formed the moon about 4.45 billion years ago, and that resulted in a remelting of the entire Earth's surface, which is why we don't find any rocks older than this on the Earth. And then there was a late heavy bombardment by comets and asteroids that again destroyed most of the early crust. And an open question is whether life began developing before or after the late heavy bombardment. And then here's just a summary of all the timelines that we know about. Now, it's 5 minutes to 8, and I think I was supposed to end in time for some questions, but I would be very glad to take questions now or from anyone. Yes, so
Okay.
Please type your questions in the chat, and we'll try to answer them.
Okay, thank you, Galen. I do have a couple questions that have come in. One was about, you mentioned an S process a couple of times.
Yes.
S process. Can you explain what that is?
Okay, yeah, the S process, so this goes to the Burbage, Fowler, and Hoyle paper in 1957, which talked about all of the various processes by which hydrogen and helium are fused in stars to make all of the other elements that we know about. The S process is a particular phase of nucleosynthesis, as we call it, that occurs in late stages of solar evolution. S stands for slow. It's basically a slow addition of neutrons onto existing nuclides to make heavier and heavier elements. It contrasts with the R process, which is a rapid process, which occurs in very violent astrophysical processes, such as the collisions between neutron stars. The S process contributes a lot, but not all, of the elements that are heavier than iron in our table of elements, and the R process contributes the remainder of them. But this was all thought out and calculated in 1957 by Burbage, Fowler, and Hoyle, and lots of work has been done, of course, since then by lots of other people. But basically, the S process started out with that paper in 1957.
Okay, thank you. All right, I have a couple of other questions. One, at the beginning of your talk, there was a short video that that brought up a question that was, what is the sun's movement like in space?
What is the sun's movement like in space?
Yeah,
right.
We're all familiar with the Earth's movement around the sun, but what is the sun's movement like in space?
So yeah, the sun is an outlying citizen of the Milky Way galaxy. And the Milky Way galaxy rotates about its center once every 200 million years or 300 million years or so. We don't have a good precise number for that. So the motion of the sun is part of the rotation of the entire galaxy. So we move along with our neighborhood in a very long orbit around the galactic center.
Okay, and I guess then what is the galactic center's movement like in space then?
Right. So the galactics, our galaxy is also moving through space, and it's moving towards what we call the Great Attractor, a supercluster in towards the constellation of Virgo, and it's moving with. I mean, all of these motions add up. The total speed of the Earth through adding up our motion around the sun's motion through the galaxy, and our galaxy's motion towards the Great Attractor runs to about 600 kilometers per second. So we're really just speeding along there, and of course we don't feel a thing, do we?
That is 600 kilometers per second, you said.
Yep.
That's a lot. Okay, that's pretty fast. Okay, cool. And one more question. The Greeks thought that the Earth was infinite, but later thinkers thought that it had a beginning. Can you reiterate why people started thinking that the Earth wasn't infinite?
I think, yeah, so, I mean, infinity is a hard concept to wrap your mind around in the first place. And, so there's always been this tension, kind of a Zeno's paradox type thing between the question of no beginning or a beginning. And I think particularly in terms of the 19th century developments, people were aware of things that ran down, processes that start but couldn't continue for one reason or another. And of course, this comes into the second law of thermodynamics and so forth, that there is no such thing as a perpetual motion machine, that there's always some dissipation that wastes energy. And so things always kind of run down. And I think that's kind of it's the Victorian age had these two contrasting impulses. One that civilization was developing on and on and on, but on the other hand, nature was grinding and grinding and grinding down to a halt, and so forth. And so both those things kind of focus people's mind on the notion of a beginning. And also, of course, there were these religious creation stories, like the Genesis story, like the creation stories that the Greeks themselves had, or the Norse mythology, or any of the other, the Apaches and the Mayas and everybody basically had creation stories where basically they were trying to explain to their grandchildren around a campfire how things came to be, and those all involved the notion of a beginning. And so the notion of a beginning, kind of came. I mean, the notion that the Earth was infinite was more a Greek thing, that things are ideal and things can just go on and on forever. And, of course, the world as they knew it, they had their city-states, they had the little battles in between them and so forth, but things were kind of constant and predictable. And as the course of history went on, this is more of a philosophical discussion than a scientific one, but it's fun to engage in it anyway. So the question of a beginning, that's interesting, and then of course, we have this great cosmology that we've developed over the last 50 to 70 years of the Big Bang, which was initially criticized by a lot of the more humanistic, rationalistic scientists of the time as resembling too much traditional creation stories. So they kind of, people like Fred Hoyle and Narlikar, Jayant Narlikar, rejected it from, sort of anti-religious reasoning. But, we have very strong evidence, both that the Earth has a finite age and that the Big Bang, occurred 13.8 billion years ago. So yeah, I mean, there's a certain point where your philosophical speculations have to give way to evidence-based reasoning.
Okay, thank you. It is now after 8 o'clock, so if you want to end, thank you very much for attending. Galen, if you're interested in, if anyone has any other questions to ask you, if you want to stick around for a few minutes. If anyone does have a question, you can raise your hand. There's a little raise hand button, or chat me and I can unmute you and you can ask your question live to Galen. So thank you again for joining us. I hope you will join us again for another PEEC talk. Look for an evaluation that will be sent to you, and I hope we do hear your thoughts about this talk so we can make future ones better for you.
Okay, can you hear me?
Yes.
Yes.
Okay, so many people would say that obviously the age of the Earth is considerably less, like a few thousand years old. And the only thing that I've seen here that really gives you or pins down the dating is radioactivity. And so some people would say, well, in the past, radioactive decay happened at different rates than it does currently. And that's why the age appears to be so old. But in fact, it really isn't, because thousands of years ago, the radioactivity happened at a different rate. So what would you have to say about that?
Okay, so so that's an ad hoc argument which constructs a hypothesis basically in order to save a theory that that they already believe in without you know, and that can't be supported by other external evidence. Now, we have great confidence that that radioactivity, the constants that determine radioactivity are things like the fine structure constant, the charge constants, and so forth, and these are measured very well in the laboratory, and they have been measured for at least 100 years, and there's been no change during that time. Moreover, we can determine by observations of very distant objects like quasars that that those constants cannot have changed by any significant amount between the time that the light was emitted by those quasars several billion years ago and the present. And so I think we can rule out that ad hoc argument as a solution to the young Earth problem.
Does that answer your question, Rick? No, he turned himself off, so I guess so. I have a question that says, where was the Murchison meteorite at the very end of the talk found?
Oh, where was it found? That stumps me for now, but I can bring Google to the rescue. It was found in Victoria, Australia.
All right, so this is Chick's question. The Earth's uranium abundance exceeds that of the sun. This is thought to have been due to a collision. When might this have happened, and does it affect the age?
Okay, I'm not sure about that premise that the Earth's uranium abundance exceeds that of the sun. I thought, in the first place, it's rather difficult to measure the uranium abundance of the sun because uranium is pretty heavy and doesn't show much in the atmosphere of the sun except through some of the molecular lines, and I'd have to I don't know that that's true. That there might have been a collision, he's suggesting, with some other body than the one that formed the moon. I don't know. I mean, the moon is pretty much like the Earth, and I think we understand the chemical composition of the moon in terms of the collision that has already been proposed. I don't know if there is a second collision proposed of yet another body for the Earth. I've not heard of that, and I really don't know how to answer that question.
Okay, so Chick, if you want to discuss that further with Galen, you can email him privately and you guys can talk about that more. Otherwise, if there's no other questions, I want to thank you again for joining us for PEEC's second live stream astronomy talk. We do plan to keep doing these as long as the Nature Center is closed. Yes.
Yes. So in fact, I'd like to advertise. So Paul Arendt is gonna do a night sky talk next week. And then either myself or Aichin will give a talk on the 10th. And if Aichin does it, it will be on galaxy and star formation. If I do it, it will be on New Mexico telescopes. And then Rick is going to give a talk after those two talks on planet formation, which is very relevant, of course, to this topic. And so maybe Rick can answer Chick's question.
Okay, thank you. Yeah, so please tune into those and do check PEEC's website, peeknature.org, for daily activities for you to do outside during the closure. All is not lost. You can still go outside. And you can still learn about astronomy. So thank you so much, Galen. And we will end it here. And thank you all for joining us and have a great night.